if you're listening to this, and I'm assuming you survived 6-6, which I'm glad. That was a tough section. You'll enjoy this one. This will be a nice change of pace. What we're going to talk about is approximating definite integrals with Riemann sums. So definite integrals, right, is the area under a curve. And we know how to find it, right? You integrate the function, you plug in the upper bound minus the lower bound into the integral. Well, sometimes functions can't be integrated, or sometimes we're not given the actual function. We're just given like a graph or some data. So we can't find the exact areas, but we can still approximate the areas. And one of these methods is called Riemann sums. And what we basically do is we take the area under the curve and we divide it into rectangles. We find the area of those rectangles, and that gives us an approximation of what the definite integral would be equal to. It's not exact, it's not perfect, but it gives us an approximation. So here's an example of what this might look like. So it says approximate the integral from 0 to 10 of f of x d of x by adding the areas of the 5 rectangles shown. This is called a midpoint Riemann sum. Okay, so if you look over here, they have this graph. They also over here have this table that goes with it. I don't know what f of x is, so I can't actually integrate it and find the exact value, the exact area. But if you look at those rectangles that are drawn, we're going to approximate it by looking at that. Okay, so this is pretty simple. We know how to find the area of a rectangle, right? This one is 2 by 2, right? We can look on here. By the way, a midpoint Riemann sums is, if I look at this first segment, if I go across here, I go halfway. So this is going from 0 to 2. If I go to 1, it's the height at 1. That's where they got the height of that rectangle is. So look over here at 1, you see how the y value was 2. So that area would be 2 times 2. All right, let's go to the next one. So if you look at that next segment right there, it goes from 2 to 4. So the midpoint would be at 3. So look right there. The height there is 5. Right, you can see it right up there at 5. So it'd be 2 times 5. I go to the next one. It's going from 4 to 6. So the midpoint would be 5. So the y value right there at 5 is 3. That gives you the height. So that'd be 2 times 3. From 6 to 8, the midpoint is 7. At 7, the y-coordinate is 1. And the last one from 8 to 10, the midpoint is 9. At 9, the y-coordinate is 3. So the graph is up there at 3. Okay, you'd multiply all those and come up with it. If you want to, a quick shortcut, if the intervals are even, like this one says you're using, these 5 rectangles are all even, right? They all have a width of 2. You could do this as a shortcut. We could just take 2 times and just take all of the y values, the 2 plus 5 plus 3 plus 1 plus 3, right? Come up with our answer. So what do we get here anyway? That's what, 7, 10, 11, 14, so 28, I think would be our approximate. So we would say that definite integral, it wants us to approximate it. I'd write it this way. The definite integral from 0 to 10 of f of x dx is approximately, make sure you use approximate symbols, is approximately, now I forgot where he put, was it 28, I think? So it was approximately 28. Okay, let's look at this example too. We're still using the same function, but now, so read through that with me. Now it says, approximate by using 5 rectangles of equal width. Hey, by the way, it tells us this n equals 5. N is the number of rectangles. To find the width of them, I know this one's pretty easy, but sometimes it gets trickier. All you do is take your upper bound minus your lower bound. So I'm going from 10 to 0 and divide that by how many rectangles we're doing. Okay, so 10 divided by 5, that means my equal width is 2, which I know you guys all figured that out already without using that little formula, but sometimes it may not be quite so obvious. So if you always subtract the upper limit minus the lower limit divided by how many rectangles there are, that tells you the width of each one. Okay, this one says a left Riemann sum though. So let me show you what that looks like on this graph here. So left Riemann sum, we start with, so we're going from 0 to 2 as my width. The height is determined by the left side of the rectangle. Well, in this case, the left side is equal to 0. I don't know if you can see that table up there. Right, at 0, it's equal to 0. So this one really has a height of 0. Since they have equal widths, I'm going to use my shortcut. I'm going to take the width, which is 2. All the rectangles have a width of 2, and the first height is 0. Okay, for the second height from 2 to 4, you go up the left side up to there. That tells me the height. So that has a height of 4. In other words, if you look up here, when x is 2, the height is 4. Okay, go to the next. It's going from 4 to 6. So go up the left side. At 4, the height is also 4. All right, so we're going to get that same that same height as the previous rectangle. At 6, so we're going to go from 6 to 8. So 6 determines the height because it's a left Riemann sum. So I go up to there. It goes from there. So at 6, the height is 2. And then from 8 to 10, you're going to go up to there. So that height would be 2 also. Right? At 8, the height is 2. So you can see how that looks different than the midpoint Riemann sum. So you can do a midpoint Riemann sum, you can do a left Riemann sum or a right Riemann sum, and all that determines is how are you determining the height of the rectangle. If it's a midpoint, you look at the middle of the rectangle, the middle number, and find the height of that middle number. If it's a left, you find the height on the left side. If it's a right, you find it on the right side. Let's see, so that come out to be 4 plus 4 plus 2 plus 2, that's 8, 10, 12 times 2 is 24. So we would say, that definite integral from 0 to of f of x from 0 to 10 dx was, according to that calculation using a left Riemann sum, came out to be approximately 24. That's what it worked out to be. So pay close attention to that, whether it's midpoint, left, right Riemann sum. So here we're going to have a right Riemann sum. This one's tricky because it does not have a graph for us. So we'll have to think about this and find it. It says, approximate the integral from 0 to 10 of f of x using a right Riemann sum. Use 4 subdivisions using the table on the right. So this one is not, notice it does not say use 4 equal subdivisions or 4 even subdivisions. So what I'm going to do is my first subdivision, because these are the numbers I have, I'm going to go from 0 to 2, and then from 2 to 5, and then 5 to 9, and then from 9 to 10. Those are going to be my 4 subdivisions. So in this case, I can't use my shortcut because the width is different in each one. So that first triangle, I'm going from 0 to 2. So the width of the rectangle would be 2. And then it wants me to use a right Riemann sum. That means I'm going from 0 to 2. The 2 would be the right. And so the height there would be 8. That's my y coordinate. Okay, look at your next interval. It's going from 2 to 5. So the width is 3. And I use the right side. I use the 5 for the height. It was 2. Okay, then I'm going from 5 to 9. Okay, that width is 4. And the height is whatever my y coordinate is right there, which is actually a -1. And we can have negative area. Remember, a definite integral is the signed area under the curve. So if it's below the x-axis, we count it as negative. And then I'm going from 9 to 10, so my width is 1. And the height is whatever my right side was, which is the 10, so my height would be 0. Okay, add this up and I get my answer. It'd be 16 plus 6 is what, 22, plus a -4 would be 18, plus 0. So I'm pretty sure that comes out to be 18. So I'd say that you guys can correct my arithmetic if I've done something wrong there. Pretty sure though, my brain's working right. Wouldn't guarantee that. It comes out to be approximately 18 units. Let's look at this next example. So example 4. So approximate the definite integral from 0 to 6 at the square root of x squared plus 10 dx using a midpoint Riemann sum with 3 equal subdivisions. Okay, so a couple important things. This one does say 3 equal subdivisions. So that means, right, I'm going from 0 to 6. So if I take 6 minus 0 and divide it by 3, that will tell me the width of each of our rectangles. So 6 minus 0 is 6, divided by 3 is 2. So I know my width is 2. We have our graph over here. So that means I'm going from 0 to 2, and then 2 to 4, and then 4 to 6. Those are going to be my 3 subintervals there. Okay, and then we're just going to, it says to use a midpoint Riemann sum. So in this case, I don't have a table. Now, if I go to the midpoint, the midpoint between 0 and 2, the height would be right there. Like this is what it's going to look like right there, right? So I got to find that height. When x is 1, what is y? Well, we could guesstimate that, but we don't have to because up here I have a function. I can plug 1 into here and find exactly how high that is. So if I plug, right, f of x equals my function that I'm trying to approximate the integral of is this. So I can plug 1 into there. 1 squared is 1. 1 plus 10 would be 11. So it comes out to be the square root of 11. That's that height. Okay, so let's do this. Because my width's the same all the way across, I'm just going to go 2 times, and I'm just going to put each of my heights in there. So my first height is square root of 11. Okay, next one, if I from 2 to 4, it'd be right there. That's what it's going to look like. I got to find that height, so that's what x is 3. So plug 3 into there. That would be 3 squared is 9. 9 plus 10, 19. So this would be plus the square root of 19. Okay, the last one is at 5, which is right there. So it's going to look something like this. Right? These are the areas I'm finding. So let's plug 5 in there. 5 squared is 25. 25 plus 10 is 35. So square root of 35. Okay. And that should give me the approximate. And by the way, there's nothing wrong with just doing each rectangle separately, right? 2 times the square root of 11, 2 times the square root of 19, 2 times the square root of 35. Like, that's fine. Either one of those is okay. This one just saves you a little bit of time, but it only works if you're doing equal subdivisions. If you're not doing equal subdivisions, you have to calculate each rectangle separately because each one will have a different width as you go across there. All right, so we got this one right here. It says, approximate the definite integral from negative 10 to 5 of 2 to the x minus 8 dx by using 5 right-hand rectangles whose widths are determined by the intervals separated by the following x values. So that means I'm going to go from negative 10 to negative 4, then from negative 4 to 0, and then 0 to 2, 2 to 3, 3 to 5. These are not equal widths then, so I'm going to have to do each one separate. It does say, another important thing is it does say it's a right-hand Riemann sum. So I'm going to start out, I'm going to go from negative 10 right there to negative 4, which is right there. And it's a right-hand Riemann sum, so that's going to determine my height. So it's going to look, that first rectangle is going to look something like that. So I got to find the area of that rectangle. Well, the width is easy. I'm going from negative 10 to negative 4. The width is 6. And then I'm going to times that by whatever my y value is at negative 4. Well, if you're not sure what it is, plug it in here, right, like we did before. Like my function is 2 to the x minus 8. So if I plug in a, a negative 4, I get 2 to the negative 4 plus 8. And you can calculate that if you want to. I'm just going to leave it just like that. We could. 2 to the negative 4 is like 1/16 and plus 8 and times. You could do all that, but I'm not going to. We're going to save ourselves times and not. Okay, the next one goes from negative 4 to 0. So now 0 is right here, so my next one's going to look something like that. Hey, by the way, this is going to come out, oh, I shouldn't have put a plus 8 in there, I'm sorry. You're probably asking yourself what I was doing. I have no idea what I was doing. Okay, it should be a minus 8. And that's going to come out to be a negative, so, right, because we're going to have a negative area down below there. This next one's going to come out to be a negative also. So that's going to be plus. My width, I'm going from negative 4 to 0. My width is 4. Times by the right side. The right side is when x is 0. So if I plug 0 in there, 2 to the 0 is 1. 1 minus 8, that'd be negative 7. Okay, next one we're going from 0 to 2. That's this one right here. It's going to be negative also. The width is 2. My right-hand Riemann sum, it's right there. It's my y value when x is 2 that's going to determine my height. So plug 2 in there. That'd be 2 to the second minus 8. That's 4 minus 8. The next one's going from 2 to 3. So that's right here. So I'm going to go plus 2 times, right? It looks like I'm going to get 0, aren't I? It'd be 2 times 2 to the third minus 8. Right, my height is 0. 2 to the third is 8. 8 minus 8 is 0. Oh, that should not have been 2, though. I'm sorry. That's a width of 1. All right, the next one, we're going from 3 to 5. So from 3 to 5, that's right here. It's determined by my right side, which is 5. So if I plugged 5 in there, I get 2. My width is 2. My height is whatever that y value is. So that'd be 2 to the 5th minus 8. And you could calculate all that. and find out what it comes out to. But that would give you an approximate to the area under the curve as you go through that. One thing to think about as we go through here, if you look at that last example, do you think, just look at this draw, of our picture over here. Just stop and think about this on your own for a second. But do you think that'd give me an overestimate or an underestimate? Talk to the person next to you real quick and decide together. Do you think that's going to give you an overestimate or an underestimate? This one's kind of hard to judge. I think this would be pretty accurate. You've got some extra here, but you're missing some there. You've got some extra here, but you're missing some there. This would be pretty close. What if we made it a right Riemann sum? So we went from the right side. Would that be an overestimate or an underestimate? Now, that's pretty clear, right? That would be an overestimate. Your approximate would be too big. What if we did a left Riemann sum from this side? So we went for left Riemann sum. That would be an underestimate. Because of the shape of the function, I think that's what happens. I think if you change the concavity and went something like this, then what would happen to our right Riemann sum on that one? So you can kind of think about what happens. Sometimes these aren't going to be perfect. They're not meant to be perfect. They're meant to be approximates. Some of them be more, some approximates will be more accurate than others. Sometimes a lot of times doing a midpoint will be the most accurate out of the three. But there might be times when a left or a right might work better. It just depends on the function and what you're looking at. Anyway, hopefully this is a nice change as compared to that last lesson that we did. I know that was pretty intense. You should be watching this on Thursday. I'm gonna give you Thursday and Friday to work on this one. That's probably too much time for just one section, but that gives you enough time to go back and make sure you finish up any other sections that you have. Make sure as you go, you're keeping track of questions. Send them to me. I will do my best to get some question answer videos out to you and try to help you out the best that I can. All right, thanks guys.